Hello, everyone. This is Shan Tian from the Advanced Power and Energy program at University of California, Irvine. So my talk today is about characterizing and comparing the vehicle-to-grid induced battery degradation in different electric vehicle classes. To confront the climate change and the air pollution, two pathways have emerged to mitigate the release of carbon. One is to integrate renewable energy into electric grid, and two is to replace internal combustion engine vehicles with zero emission vehicles operating on low or zero carbon fuels. So transportation sector accounts for 40% of greenhouse emissions in California, and 92% are from petroleum-based fuels. California, as a leader to realize its vision of a carbon neutral economy, sets a 2045 goal of powering all retail electricity sold in California with renewable and zero carbon resources such as solar and wind energy. Due to the intermittency of renewable energy storage is required to support the future electric grid. So modeling results should suggest that the capacity of stationary energy storage technologies, such as stationary batteries, is insufficient to store projected excess of renewable energy. In order to meet the demand, battery storage build rates needs to increase by nearly 8-fold. On the other hand, California is moving towards having 100% of new cars and passenger trucks sold in the state be zero emission by 2035. So these large onboard batteries emerge as an opportunity for a grid support energy storage and to support the renewable integration. As an introduction of the definition, the vehicle grid integration is any method of altering the time, charging level, or location at which grid-connected electric vehicles charge or discharge. And V1G, or grid-to-vehicle, is defined as single directional charging that allows managed charging and flexible demand. One example is smart charging that manage the charging of EVs in an efficient way where charging can be shifted based on grid loads or the vehicle owner's demand. And vehicle to grid is bidirectional charging and discharging that allows vehicle to discharge stored energy back to the grid or into buildings or into local power systems. The benefit of vehicle grid integration is that it can provide additional revenue to lower the total ownership cost for EV owners or fleet operators. So this graph here shows the total benefits from a lot of use cases defined by California Vehicle Grid Integration Working Group. So X-axis shows different use cases, and the Y-axis shows the total statewide benefits in the near future. As can be seen, total benefits from light-duty vehicles use cases are in general higher than benefits from medium and heavy-duty vehicles use cases, due in part to higher assessed EV populations for light-duty vehicles in the short term. Aside from monetary values, VGI can increase the renewable penetration when updating a given reduction goal for greenhouse emissions. It can also reduce the ramping rate of power plants by shifting the load and reducing the peak demand. As a result, V2G can help reduce the fossil fuel usage, especially at power plants' low efficiency operating periods, to reach a further reduction of GHG emissions. However, VGI do have drawbacks and may raise concerns for the customers. So one major issue is the potential of accelerated battery degradation due to V2G. various factors such as charging rate can impact the degradation. Charging rate is grouped into 3 categories based on charging power: level 1, 2, and DC fast charging. Increase the charging power will increase the charging rate and reduce the charging time. In the graph here, the using level 2 charger at home will significantly increase the battery degradation due to higher C rates and overall energy output. So the location will impact the available dwell time and the charging duration. So it will further impact the battery degradation. The other factor is the grid application and the service frequency that the vehicle battery performs. So net load is the system-wide load profile minus the generation from intermittent renewables. So load shifting or shaping aims to mitigate the fluctuation of the net load by filling the valley and shaping the peak. But frequency regulation maintains the frequency of the grid for a short time. So it helps match generation and demand and adjust generation output to maintain the desired electric frequency for the grid and function normally. So degradation is sensitive to the frequency of providing services. For extreme cases, the degradation from net load shaping is relatively higher since the overall energy throughput is higher. But for frequency regulation and peak load shaping, it's not accelerating battery degradation significantly in comparison to the degradation induced from driving and calendar aging. So previous studies have focused on VGI of light-duty vehicles as they are early adopters, and they are suitable for VGI because they have more than 90% of idle time, but they have drawbacks like relatively small battery capacity per vehicle. And in order to aggregate a large fleet of vehicles, the public perception and social behaviors have to be considered. But for medium-duty vehicles and heavy-duty vehicles, they have larger battery capacity per vehicle, and they're usually operated by fleet, so it's easier to aggregate and provide services. So in this study, the vehicle categories are defined as light-duty vehicles and light heavy-duty vehicle, medium heavy-duty vehicles, and heavy-duty vehicles. So unlike passenger vehicles, medium heavy and heavy-duty vehicles are usually designed to be used for 7 to 12 hours and are primarily part of operating a business or public service. So for heavy-duty vehicles, drive cycle is a critical factor. So this study will characterize and compare the VGI impact on different vehicle classes based on their own duty cycles. In order to analyze the duty cycle, the holistic grid resource integration and development tool will be used. HiGrid is a multi-module platform that simulates the dispatch of grid resources to meet electric load demand in California. So HiGrid establishes the emission impact on the electric grid. It also indulgently determines the duty cycle of vehicles since the vehicle modules are built in within the tool. So in the EV module, the energy demand is determined by the vehicle trip data and vehicle parameters such as the trip start and time, distance traveled, and the vehicle type and efficiency. And the charge discharge profiles are determined by the dwell time and locations and the power level of the infrastructure facilities. So vehicle parameters, chip data and infrastructure parameters will determine the energy demand and charging profiles. To integrate the EV module with other modules in high grid, the energy demand is translated to energy consumption and further added as additional load to the net load as charging demand. And depending on the available energy capacity remain in the battery and the net load signal, the this charge algorithm will be used to decide whether to charge or discharge. So this algorithm has a goal to minimize the total charging discharging cost by discharging at the high electric load period and charging the low electric load period. The constraints are to ensure that by the next vehicle departure time, the vehicle stay at its full state of charge. And for each activity, the battery operates within the range of 0 and full capacity, as well as the charging rates should not exceed the power level. As can be seen in the graph, the state of charge profiles varies within each fleet and of course across different vehicle categories. The state of charge profiles are different because of their different travel patterns. Once the state of charge profiles are obtained for each vehicle, the profiles of each individual from high grade will be input into BLAST, which is the degradation analysis tool that I will introduce in the next slide. So battery lifetime analysis and simulation tool developed by NREL contains 3 submodules: thermal, electric, and degradation module. It's based on the empirical fit model of NMC lithium-ion batteries, and they will forecast the reduction in battery degradation and increase in battery resistance based on the inputs of voltage, state of charge, temperature, and C rates. So battery degradation distribution graph, as I show here, is aggregated after the outputs of BLAST. So each run BLAST will output the remaining capacity after 10 years. So I aggregated all the results for light duty vehicle fleets and plot the degradation distribution here. As you can see, the majority of the fleet degrades within an acceptable range, which is less than 20% in 10 years. It suggests that if the remaining capacity is less than 80%, there is at least one replacement needed for vehicle lifetime. And for heavy-duty vehicles, almost half of the fleet degrade more than the acceptable range, which means around half of the heavy-duty vehicle fleet needs battery replacements during their lifetime. And the worst case can experience more than one battery replacement, since the least remaining capacity can be as small as 20%. So the reason might be the difference in their travel pattern and their availability for vehicle to grade. Also, the charging intelligence level will impact the battery degradation. Smart charging has less impact on battery degradation since only shifts the charging time, but not necessarily imposes more cycles to the batteries. The accelerated battery degradation from V to G is different for vehicle categories. In reality, the remaining capacity is never going to go down to 20% since the battery will be replaced once reach 80%. So the next step is to further interpret the results with replacement constraints. And thank you all for watching this video. And if you have any questions, please feel free to reach out at the email provided here.